Welcome to today's colloquium. It's a great pleasure to introduce today's speaker, Professor Laura Greene from University of Illinois, Urbana-Champaign. Professor Greene has chosen to talk about high-temperature superconductivity. Let me first tell you a little bit about her background. If you really are interested in more details, you are welcome to read 56 pages of the CV describing how busy she is. In a short few words, Professor Greene is doing experimental condensed matter physics. She's investigating strongly electron-correlated materials. In particular, she's focusing on two different areas. One is unusual superconductivity, the mechanisms that lead to unusual superconductivity on one hand, and in particular investigating experimentally symmetry-broken states in the superconducting materials. And then in other areas of research, she's investigating interfaces between superconducting and non-superconducting materials. And her favorite tools are electron spectroscopy using planar tunneling junctions, as well as electron injection through orifices, which is point contact spectroscopy. We will hear about that. But this is only part of her many activities. Professor Greene is enormously involved in scientific community in the broadest sense. She's an advisor to many scientific boards, particularly in the very high-level boards in the United States. BSAC, Basic Energy Science and Advisory Committee, and many others as well internationally. She's also the chief editor-in-chief of an important international journal. Of her many, many accomplishments and honors, I may just want to mention a few of them. One is a Guggenheim Foundation Fellowship. She's a member of the National Academy of Sciences. Since 2000, she's a Svanlund Endowed Chair at University of Illinois. In 1999, she was awarded the Materials Research Prize, the Lawrence Prize of the Department of Energy in the United States. And of the American Physical Society in 1994, she was awarded with the Maria Goeppert-Mayer Award. These are just a few of the many international recognitions she had. Professor Greene was one of the early pioneers in high-temperature superconductivity, and she has seen how the field developed over the last 20-plus years. And as we know, every now and then, every few years, new classes of materials are discovered with great surprises, and superconductivity at high temperatures is discovered in materials that until now were not thought to be very favorable for superconductivity, for instance, because they were magnetic. And this serendipity in finding new materials, she will tackle today in her talk, in particular because she is part of a board thinking about this, how to tame this serendipity. That shows you when she was at the very beginning of high-temperature superconductivity together with her laboratory assistant, Bill Feldman. That was in early 1987. So she knows what she's talking about, and I would like to welcome Laura Greene here. Thanks for coming a long way, and we're looking forward. Thanks a lot, Laura.
Oh, thank you for inviting me and for that incredibly embarrassing introduction. This is, let's move on from here. Anyhow, so the title of my talk is Taming Serendipity. And the whole point of what I'm going to, is this too loud? Or no, I'm hearing myself. Anyhow. I normally have a very loud voice. I wouldn't need a microphone at all. But so what I'll be talking about is how we don't know how to design new superconductors. We don't know how to design any kind of strongly correlated electron materials. So this is really going to be a speech that's sort of more educational, and only at the end I'll talk about some of my own work. And Bertram, my CV is not 56 pages, it's 75 pages. So So these are some of the applications that especially the Department of Energy is worried about. One is superconductivity as an energy carrier and how we could impact the electrical grid. And I'll also mention as superconductivity as an energy generator and how it helps us in turbines. And also something called SMEs, superconducting magnetic energy storage devices, and how important they will be for energy storage and for smoothing out the power in the grid. Our playgrounds are the periodic table to try to make new materials, and this is sort of something I stole off of somebody's website on the web to show that we're also trying to understand the mechanisms of high temperature superconductivity. And I'll have a little bit more to say about that. Since this is a general colloquium, oh, by the way, this was my journal celebrated 100 years of superconductivity. Now it's 101 years old, but you know, that's in the noise. And so I'll just remind you quickly what a superconductor is, because being at ETH, I'm sure most of you know, and why we need better and newer superconductors, not just higher temperature, but also higher current carrying, JC, current density carrying superconductors, because if you can't carry current, it's no good for applications. And then I'm going to spend some time on the history, because the history is very interesting, and how serendipitous it's been to discover new superconductors. A charge is like, this is my world peace view graph. I'll show, there's two of them like that. I'll mention somewhere in here a center that I'm co-directing for the Center for Emergent Superconductivity, one of the Energy Frontier Research Centers. And then I'll spend a little bit of time talking about renewables, what I mentioned earlier, the applications of superconductors. And if I have time at the end, I'll mention some of my own work. I'll just start to tell you what a superconductor is. It transmits electrical current without loss, power without loss, which means if you have a superconductor in carrying current between a battery in Zurich and a light bulb in Paris, you wouldn't need any repeater stations. It would transmit energy without any loss at all, without heating. And so obviously that's going to have tremendous impact on energy carrying of electricity. And also perfect diamagnetism, and which I'm not going into here, is another fascinating property of superconductors as long-range quantum mechanical order. The applications of diamagnetism are obviously education. We can levitate things. And in fact, superconducting levitated trains have been around since the 1980s. My Japanese colleagues have had a levitated train that goes with conventional superconductors, niobium titanium, since the early 80s, went about 1 kilometer. They always told me unabashedly that it just went only 1 kilometer, but that was long enough to take their funding agents for a ride. But in fact, people are making levitated trains out of high temperature superconductors, and here's one that's a prototype in Japan. An advantage of levitated trains is you don't have a limit on the speed. A train can only go so fast, so the friction can overcome the wind friction. And in a levitated train, it's basically a rocket. And if you're trying to levitate trains with magnetism, like in Shanghai, that has its own difficulties because that's inherently unstable. But because why this one here levitates, this superconductor levitates, that the levitation, unlike permanent magnets, this is inherently stable due to pinning of the vortices. So there's real practical applications in this. So why do we need better superconductors? First of all, this is really a great unsolved problem. Okay, it took superconductivity discovered in 1911. The microscopic theory for simple S-wave metallic superconductors was discovered in 1957. Right, that's the BCS theory. And there is no other theory that I know of that really transformed, that I can tell, theoretical physics like that one did. But so it's amazing stuff. But they're playgrounds for all kinds of things like quantum criticality, broken symmetries, but we don't know how to design them. And as far as broken symmetries go, I'll just mention superconductivity breaks gauge symmetry inherently. The high temperature superconductors are D-wave, so maybe you've seen that before, but they break a certain kind of rotational symmetry. And then those things will also inherently at low temperature break time reversal symmetry because of things which I don't have time to go into here, but they are really fun. So high temperature superconductors are fascinating, crazy, and for fundamental science they're fun, but what about applications? Many applications exist. So superconductors are used in MRI. They're used for high frequency detectors. That's the long range coherence. Superconductivity is intrinsically voltage frequency mixers, and so they are the frequency standard for the world in Josephson arrays. They're used for cell phone filters. They're used in fusion research. Better superconductors would be transformatives for renewable energies, as I mentioned, the grid, the turbine, and superconducting magnetic energy storage. This is a picture taken by my advisor for my postdoc at Bell Laboratories, John Rowell, and this is what we call the Ellie-Ashberg function. This is the order parameter. This proved the BCS theory of superconductivity. That's it. Okay, so that's the fundamental part. And here's niobium 310 that's used in the ITER project in France for high energy, nuclear fusion energy. So this is another application that could be very important. Right now, this is US oriented, but it's been called by the National Academy of Engineering that the energy grid is the triumph of 20th century engineering. I will also add that it's 19th century engineering. It's just a bunch of cables. And what we have here is this is kind of representing the grid, but this is really the Eisenhower highway system, because that's what you can see from space. But in fact, what you can see here is that there's these blank spaces here, and then there's a lot of brightness where the cities are. Now, if we want to use renewables that will be traveled on the grid, okay? In other words, we don't want to like cut the trees down and carry them on trucks somewhere, right? That's not good for the environment. What we want to do is mine solar energy, and we want to mine wind energy, and maybe geothermal, but we see that the demand is at the extremes. So what's going to happen is we're going to stress the grid even more, and that becomes a problem. So breakthroughs are needed to make the grid ready for renewables, for long distance, reliable, efficient delivery of electricity, which is a clean and sustainable energy carrier. For those of you that buy your Energy Star refrigerators and feel so proud of yourselves, I want to just show you that at least in the United States, 40% of energy is devoted to electricity production. Look how this has gone from 1900 to now where we are now. We've gone to about 3 or 4% to like 40%. This is a lot of energy, and that really stresses the grid. And the 21st century has to be thinking differently. In Illinois, we're putting a lot of effort on the grid, and there's a lot of work on how to redesign the power grid, smart grid, because it is 19th century engineering. And one of the things that could have a major effect is putting in superconductors as an energy carrier. Let me show you some of the problems we have, and that is that the growing demand, there's a capacity going into the cities from the long lines. It's just, I'll show you a picture coming up there. You really have a bottleneck. And even the superconducting cables that exist today, and I'll show you later on, 2% of the cross-section of the cables that exist today are superconducting. 2% of the cross-section is superconducting, yet they carry 5 times the power of copper at the same temperature. So superconductors will have a tremendous effect on the bottleneck and the ability to carry current in smaller areas. Reliability and quality. This is something that is amazing to me. We lose $79 billion a year in losses in the grid. That's resistive losses, brownouts, and blackouts. That's all the loss together. $79 billion a year. That's a lot of money, okay? But anyhow, also, as we start accommodating renewables, if we start putting in more wind and solar and other kinds of energy, and we want to transmit more of that on the grid instead of putting them on trucks or pipelines or trains, because again, this is a clean and sustainable energy carrier, right? That's going to stress the grid even more. The United States has a goal of having 17% of its energy being from renewables by the year 2020. Let's see how the election goes. So this is a nice picture. This is back in 2008, but I just love these pictures here, and nothing's really changed. This is in Manhattan under William Street. It's just like a rat's nest, like my hair used to be before I straightened it. And so these are all these cables in here, and it's just a mess. And that's part of the bottleneck. And nowadays, we have two companies in the United States, Superpower, and this is American Superconductor here, that can actually make long quantities of reliable, high current carrying superconducting wires. They're amazing, but they have their limitations. Some of the I'll just tell you, I think the biggest limitation is the expense. That's going to become less because we need this so much. The real problem is how long it takes to manufacture these things, and they produce less than 1 kilometer a month. So someone calculated how many years it would take to string one of these cables across the United States, and it was, I forget, but it was something that I'm too embarrassed to remember. The Korean government has put in to Superpower a huge request to buy a lot of the superconducting cable, and Superpower is really scrambling. They're probably not going to make that demand. So there's real limits to what we have, even though these materials are awesome. What's been accomplished in producing these wires is amazing. They're still limited, and we need to do better. One of the things that's happened in the United States is our energy frontier research centers. And so I just want to advertise mine a little bit and them in general. There are 46 centers around the United States. Okay, and the commitment is $777 million over 5 years. We're almost 2.5 years into this project. Let me step back and say that in the United States budget, $777 million over 5 years is probably peanuts, right? We just saw what was lost in the grid in a year. However, I will state also that this amount of funding put into research really has helped to transform research in the United States. We were really suffering for a long time. I'll go into that in a second here. This is something I've been, as Bertram said, I've been involved with DOE Basic Energy Sciences Advisory Committee for longer than I care to admit to. But what they started doing early on was doing these reports. And the first one, and by the way, these are all downloadable, and for some reason, they keep moving the website. So if you are interested in getting these freely downloadable reports and can't find it, I'm LH Greene with an E at the end at illinois.edu. I'll find it and send it to you. But the first one here was basic research needs to secure our energy future. And Smalley, who won the Nobel Prize for buckyballs, said in there that we have a real serious problem on our world energy crisis. And if we don't go at this with the same vehemence as, for instance, the Manhattan Project, we are going to be in trouble. And in fact, we all know that there is global warming. There is global climate change. Even our president and our Secretary of Energy, Steve Chu, at a conference that I ran a month ago said, yes, there is global climate change, and don't be a merchant of doubt. In any case, we're in trouble, and we have to do something about this. So what the Department of Energy did was do a systematic study of how we can secure our energy future. These are basic research needs reports. If you're interested at all, download them and read them. Each one of these reports has a history of the field, where we are now, and where we think we can go in the future to secure our energy future. And some of these are, you can see solid-state lighting, advanced nuclear energy, combustion fuels, matter at extreme conditions, et cetera, et cetera. There were 10 of these basic research needs, BRNs. But somewhere around, like between 2003 and 2005, the US wasn't going to support fundamental research. Notice I said fundamental research, not basic research. That's one of the language things we have to use, because if it's so basic, why are you doing it? So just remember that in talking to your politicians, it's fundamental research. In any case, most of these things never left the Department of Energy. I worked on this one here. I'll show you it again in the next view graph. This is the one on superconductivity, why we need it to secure our energy future. So they just got stuck. They never made it to Congress because Congress wasn't going to read them. So then we wrote this other one here, which is 5 Grand Challenges. And that was a compilation of what we thought was important, the main challenges that we can do to secure our energy future. But it was too thick, so nobody read it. And then we came up with this one. If you're going to download one, where is it? This one up here. New Science for Secure and Sustainable Energy Future. So that, what we call our new era. That came out in 2008. Talk about great timing. It's believed that the history of 10 years of writing these reports and this compilation was what defined those energy frontier research centers. And in fact, every single one of the centers is aligned with one of these topics here. Just to go a little further on here is something that I've been pushing for a long, long time, is this one here. I was on several of these subcommittees, Science for an Energy Technology. In the United States, we used to have Bell Laboratories. What was that? Anybody ever hear of Bell Laboratories? Okay, so long time ago. Bell Laboratories had a mechanism for getting fundamental research to the marketplace. We called it tech transfer, technology transfer. It didn't really work, okay? So what happened, like Jean-Marie Tarascon would invent something really fabulous, and he would himself carry it through all the way through until he had workable batteries, right? So it was a very tenuous, weak way to go from fundamental research to the marketplace, but it was all we had. With the demise of all of the physics industry-based research in the United States, there was no way to do this. And the demise of Bell Labs, IBM, Schlumberger, and a lot of these other companies has been linked to the lack of the United States being innovative in its applications and its marketplace strategies for technology. And so we're still trying to figure out what to do with that. And so this one, I think, is a good read. We haven't done it. It's new. We haven't done anything with it yet. It just came out in 2010. But the national labs aren't going to do it for you. You know, we have university, industry, and national laboratories. That's not going to work. So this sci-tech was something that I helped design, which is get people. I was in a room. My report was on energy transmission. You have universities, professors in a room with people in industry, utilities people, and even a regulator. Ooh, okay? And the idea was not what can you do for me, but what can we do together? Not how can industry fund students, not how the university can help make measurements for industry, but what are our grand challenges? And that's where I learned about SAG. You know what SAG is? In the grid, you have a brownout, and so it switches over to some other cables, and they get hot, and they sag. And they hit the treetops, and those burn out, and then the energy gets shifted to other cables, and those sag, and you can have a brownout and a blackout, et cetera. These are fascinating materials. I know it doesn't sound interesting to you right now, but it really is cool. So the whole idea to do this now is to bring people from different areas and work together towards these goals. Don't give up the fundamental research, but find a way to feed it into what's going to have a practical application to our lives and make our lives better. Then I have to advertise this one that just came out 3 days ago. This is called Meso 2012, and I just have to advertise it because I was on this subcommittee. This isn't the same meso that we talked about 35 years ago, mesoscopics, okay? What this is how do we go from the quantum to the continuum? So, for instance, I work in superconductivity, and what I will show you about in the next few minutes is that we don't know how to design superconductors or any functional, strongly correlated electron materials. How can we start from the nanoscale, which we have since learned to control, and grow those into functional materials? This also has to do with how nanocracks get growing, et cetera, et cetera. But it's kind of a fun report, and I recommend it. If you just Google Meso 2012, you'll find the report. It's been available since Tuesday, I think. Okay, so this was our report, that 2006. We were feeling really proud of ourselves. We wrote this report, never made it to Congress, but we liked writing it. And this is basic research needs in superconductivity to secure our energy future. And this is our TC versus time plot, okay? I draw it a little differently now. For some reason, so this is year, and this is temperature. That's the superconducting transition temperature below which the material is superconducting. This happened over here, down the street, okay? Alex Mueller and George Bednor's. And that led to all these other discoveries here. This here is the standard S-wave metallic superconductors. And I kind of draw this differently now that also down the street in Europe, which is in, well, it was Darmstadt, now it's Dresden. This material here is called a HeavyFermion, and it was found to be superconducting. I'll show that again later on. But it turns out that this material and all the other materials on this graph, except these red ones, okay, look the same in their phase diagram. And that's this phase diagram right here. Okay, this phase diagram, it's drawn a little differently, whoever draws it, but basically what you have here is a dome. This is temperature here, temperature, and this x-axis is either pressure or doping. All the cuprates, this was nominally a cuprate phase diagram. And so in all of these guys, okay, on this side of the phase diagram, we have something called a Fermi liquid. A Fermi liquid is described by Fermi-Landau theory. For those theorists up there, DFT works. In other words, if I give you the crystal structure with a few little tweaks there maybe for little functionals, et cetera, I can give you the electronic structure. You give me the crystal, I will tell you whether it's a conductor, how well it conducts, all kinds of things, right? If it's a semiconductor, if it's an insulator. This is something that's not that way. And when these phases compete, you have an emergent phase here. And there may or may not be a quantum phase transition down here, which is nominally a phase transition at 0 temperature. But in this case here, that domed behavior is a superconductor. I argue now that we understand this. We don't know the glue for all the superconductors, but it's all Cooper pairing. I assume we're in ETH, you know what that means. It's all Cooper pairs, right? For all these materials here, it's electron-phonon coupled Cooper pairs. For all these guys, there's probably a few electron-phonons helping and out there, and there's spin fluctuations. We need to work out the glue. But basically, we understand microscopically what's happening down here. Okay, so we know what happens to an electron that goes through there, or if we're doing heat transport or any kind of thermodynamic or transport measurement. Go into this area here, and we are clueless. That's what we call electron matter. That's what happens on the high temperature superconductors. This is this AFI here is a Mott insulator. We can have pneumatic structure, which is something that I'm measuring. If I have a second at the end, I'll show you, which is the electrons form an interesting liquid crystal-like pneumatic structure. They line up like cigars, right? And there's nothing in the underlying crystal structure that dictates that. There's pseudo-gaps. There's heavy electron behavior. There's orbital ordering. There's all kinds of things that are funny electron matter not dictated by the underlying crystal structure. So anyhow, in any case, we identified this phase diagram and we said, okay, give us enough time and we will design new superconductors. Well, nobody did, okay? So HighTC's invented 1986 down the street here, and these families come out of this thing, and there's some serendipitous behavior. And then Hideo Hosono comes up with this thing in 2008. A whole new class of high-temperature superconductors were discovered, completely serendipitously. So that's something about my center. I'm just going to go over this one. That's boring enough. Let's go into the history here, okay? So let me go over the history just because I think it's fun and it's good to, and I'm old, so I like history now. So anyhow, there's a really great article that came out in 2010 in Physics Today. And these pictures are taken from there. Well, these top pictures are. And so in 1911, Heikki Kammerlus Onus wasn't looking for superconductors. He was looking to cool things. It was called the race for the cold. And he learned how to liquefy liquid helium. And he and his technician, Holst, decided to guess what would happen if we cooled down a metal. What would happen? And so they chose mercury because mercury is a liquid at room temperature, and they felt that you can clean it up better, right? You can purify it as a liquid. And they thought purity would be important. And it was not known whether Lord Kelvin would be right, and they'd freeze out the carriers. Matheson would be right, and you'd just come in like this. Or Dewar would be right, and you'd slowly go down to zero resistance at 0 temperature. This was not expected. Okay, you've seen this plot before. At around 4 degrees, the resistance dropped precipitously. And it's a long story on how they proved it was zero resistance, because proving something is zero is hard. Fascinating history. But I like to point out that I have this press release at home. I have a copy of it. That in 1913, Kamilech Onis came to Chicago, and there's a Tribune press release where he says that because he very quickly, by the way, discovered not just TC, but critical currents and critical fields just by making magnets out of it and putting current through it. And he realized these things could make really big fields. And he said, not only by transmission, but also energy storage, this is going to impact our world energy crisis, 1913. This is a brilliant man way ahead of his time. So, this is the history of the next few decades. The superconducting transition temperature rose slowly. People just started measuring things and testing things. And most of this led in the 1950s primarily by Bert Matthias, right? And by the way, there's this great memoir written by John Hume and Ted Jabal. And also, there's a very nice article by William Pickett, like what if the first superconductor that was discovered was in fact not mercury? What if it was YBCO? So that's kind of cool, high temperature superconductor. Anyhow, I just want to point out that Bert Matthias in 1952 discovered the first new class of superconductors. He took a ferromagnet and a semiconductor and mixed them together and found a superconductor. Low TC, but wow. Okay, that was a complete surprise. And he had these rules here. Transition metals are better than simple metals. That still holds for the high TC. Peaks and density states at the Fermi level are good. And another colloquium, I go into showing how accurate this is, that you want a large density of electronic states near the Fermi level, and that helps superconductivity. That's the Macmillan equation, and holds in huge numbers of materials. So these things still hold. These next two just don't work at all for the high TC. High symmetry is good, cubic is best. In fact, the high TC materials, the more layered, the higher TC, and stay away from oxygen, magnetism, and insulating phases. All of the high temperature superconductors are, in some cases, quantum criticality next to those phases. So it's not that Matthias was wrong, it's just that he was correct for the S-wave metallic superconductors. This was before the high TC were around. In fact, towards the end of his life, he wanted to start looking at oxides, and everyone thought he was crazy, but you know, he wasn't. Brilliant guy. Concomitantly, we have John Hume doing the same stuff, only in applications. Brilliant, innovative, transformative behavior. What they did was he worked with his graduate student George Hardy and discovered the first of the A15. The A15 is an A3B structure like this, where A is a transition metal. Okay, this was important because these were the first superconductors to show a high critical current in a strong magnetic field. All the other superconductors, you put a little field on it and it just breaks the pairs apart. They're just not strong coupled superconductors. These were the first, and in fact, these A15s are the workhorses for the high field magnets that are used nowadays. They're really important materials. But Bert Matthias ran with this. And he discovered over 30 of these A15 compounds with TCs ranging up to 23 degrees. And my boss, Jack Wernick, was one of the guys that worked on this one. This is niobium-3 germanium. That's the highest TC. So the history then went on to practical wires. In 1963, 11 years later, John Hume looked at a material that was discovered by Rutherford Appleton Labs in the UK, which was a random alloy. Let me go back here. This is a compound. Compound structure is important. If you disorder this compound, you wreck the TC. If you disorder the compound, you screw up the electronic structure, and it's not superconducting. If you have a random alloy, like niobium titanium, it's malleable, right? These compounds tend to be brittle. It's malleable, and it's hard to screw up the TC. So the TCs aren't as high as the A15s, and the critical current and critical fields aren't as high as the A15s, yet these are the workhorses for the field. They're what's used in ITER most of the time, and they're what's used in the LHC. They're what's used in MRIs because they're reliable. They still have a high JC, they still have a pretty high TC, et cetera, et cetera. So that's very important, and here are some pictures there. I just like this because Jack Wernick was my boss at Bell Labs, and so when he retired, John Rowell says, high TC gets Nobel Prizes, high JC saves lives. We would not have MRIs without HighJC Materials. Okay, anybody ever have an MRI? You get to go inside a superconducting magnet. How cool is that? God. So anyhow, come along Frank Steglish, who I think he with June Kondo and maybe David Pines deserves a Nobel Prize for what they've done in strong correlations, but amazing stuff. He came up with this HeavyFermion Materials that are superconducting. HeavyFermion Materials, of which our own Bertram Batlogg is a world leader, they have rare earths or actinides. They're 4F or 5F elements. And they have an antiferromagnetic ground state. They also have very large, they're called heavy fermions because the M stars are up to 1,000 times the free electron mass. And that is not explained by the band mass. If you've taken solid state physics, excuse me, I'm a heavy drinker. If you've taken solid state physics, you know that M star is calculated by the curvature, 1 over the curvature of the band structure. You're not going to get 1,000 M star that way. So it has to do with a certain interesting kind of hybridization. The bottom line, it's a strong electron correlation effect, not dictated by the band structure. And he also showed that it has this interesting phase diagram. It's antiferromagnetic here and has a superconducting phase here. And there's evidence of quantum criticality down there. These were the first truly tunable superconductors through a competition between ground states. In this case, the heavy electron state, and in this case, the Fermi liquid. For the first time, magnetism looks good for superconductivity. The electron-phonon BCS theory has broken down. That's the glub, glub, glub. I put that in an article once. Let me just say, in my opinion, it's not held by everyone, BCS does not break down. It's still Cooper pairs. We just don't know that it's electron phonon what the mediation is, okay? I want to point out that there's certain heavy fermion superconductors that I think weren't discovered completely by serendipity. This was probably serendipity, a lot of smart thinking, et cetera, who predicted this. But some of these 115 that Joe Thompson and Zach Fisk worked on, which are cerium, cobalt, indium 5, were sort of looked at that they were materials that were strongly magnetic and superconducting, and they combined cerium and cobalt. You know, they had ideas, and without telling you what I think they were thinking, I could be wrong, they really understood these materials in a way that very few people understand them. So I don't think it was complete serendipity. But they haven't really repeated this very much, so it's not prescription, it's not predictive design of materials either. Now let's go from the history there. Somewhere along the line, Marvin Cohn and his PhD thesis decides that strontium titanate ought to be an insulator that superconducts. And he was right. If you've ever worked with strontium titanate, you just look at it funny and it superconducts. If I take strontium titanate and I rub a soldering iron on it, I can make it superconduct. Okay? It's just you can remove oxygen, dope it with niobium, titanium. It's got some interesting, and what Professor Spalding pointed out to me, maybe I should revisit that again, because it's got some interesting properties. In 1983, okay, Mathis and Hammond calculated the electronic structure of a famous superconductor called barium-lead bismuth oxide. Okay, after high TC comes out, okay, they do this electronic structure and they say, for reasons which we have discussed here, let's try this other kind of doping. And in fact, Len Mathis went into Mike Georgi's lab and grew this stuff, okay, and it was a 40-degree TC. It was lousy material. Bob Kava comes along and makes it into a single-phase 40-degree real superconductor, okay. That was probably calculated. Have we repeated that? No, so we're not quite as predictive design as we'd like to be. There's some other interesting materials. Are these the only truly theory-driven superconductors? Depending on what Bednorz and Mueller tell you or what Wu and Chu tell you, maybe. In 1988, the TC was driven up to 165 degrees in this compound here. That was 2 years, 3, 6, 7, 8, 2 years after the discovery, less than 2 years after the discovery of HighTC. HighTC is discovered in 1986. The maximum TC is reached in 1988. No new classes of superconductors come around except for 86, 22 years, okay? And that's this guy here, is that they always say that the Copper Age, Zlatko Tasanovic, who we all miss very much, was the one who said the Copper Age has given way to the Iron Age. So he was fond of saying that the iron-based superconductors broke the 22-year tyranny of the cuprates. And so Hisano, again, this was completely serendipitous. This is a chemist in Tokyo that's studying p-type and transparent conductors, right? And he finds that this material is superconducting. He recognizes it, puts a group of people on it, and in January of 2008, publishes in JACS, Journal of the American Chemical Society, this superconductor, right? And by, I would say by January, March, April, the Chinese took over, and Zhao, who's done a lot of really great work in superconductivity, basically drove this thing up to about 58 degrees by substitutions, et cetera. Beautiful work, cleaned up the theory. Not much new has happened in this sense then, a little bit. So let me also say something about funding. The Japanese government was able to put $25 million into this field between January and June. They didn't go through funding agents. It was the government. They set up a whole new way to fund this guy and to other people in that field. Was that the right thing to do? Well, Hisano has since come up with a material that's used in the iPad, was it 4 now? The latest iPad that just came out, you know, flexible electronics. It's probably the right decision. So that's very interesting now. Now, whether these materials, these iron-based materials, will be applicable or not, we don't know yet. They're very promising. But to me, what gave a shot of the arm in superconductivity is a second class of HighTC was discovered. There must be a third. And that brings us to our new charge, which Rick Greene and Laura Greene, no relation, we're doing this charge together, which ICAM is the Institute for Complex and the International Institute for Complex and Adaptive Matter. So we get together at superconductivity meetings and say, what are your ideas for designing new superconductors? And I can give you I share them freely. And so at the very first meeting that we had of this, which was probably 2008, one of my buddies said, well, why should I tell you my ideas? If I had such good ideas, why would I share them with you? And then Mike Norman, one of our buddies, said, well, if you had such good ideas, you wouldn't be at this conference. You'd be home doing it. So the bottom line is it is so risky to look for new superconductors that I'm much better off measuring the pseudo gap or critical currents or, you know, quantum oscillations. Interesting, really good physics. But to put all my effort into trying to design new superconductors is a disaster for future funding. So let's share it. This is too important not to share it. And I wrote an article on this, and that's where I got the serendipity from this article I wrote in Physics World, which is world peace, let's work together, come on. Anyhow, this is a talk which I'm not going to give here, which I will share with you, but I talk about why we want reduced dimensionality. Not only do the higher TC superconductors exhibit reduced dimensionality, we have reasons why. It has to do with screening and reducing and what the density of states looks like in 2 dimensions. Tony Leggett's working on that. Transition metal and other large U ions. Hubbard U is something you can look up in a periodic table. It's how much energy it takes to remove the atom, the electron, and put it back in, minus what it takes to put back in. Basically, it tells you electron-electron interactions. And if you're going to make Cooper pairs, you better have strong electron correlations. Light atoms, that has to do with having high phonon density of states. Are phonons important? Maybe. Tunability, all of the superconductors are tunable. Charged and multivalent ions, well, that again has to do with, it looks like covalent bonding is important. And it's been guessed that if you can dope sodium chloride, if you start doping sodium chloride, you get polarons. There's really strong electron correlated things. But if you could actually turn that into a metal, that would be a really high temperature superconductor. Let me backtrack and defend that two ways. One way, the stronger the correlations on this side, the higher TC is. This is something that Zach Fisk has been saying for years. Okay, this is the chemistry side, and this is the physics side. You want those as strong as possible to have the strongest possible dome here. So people are kind of looking at, so the iron-based superconductors are not Mott insulators. They're strongly correlated, but they're not as strongly correlated as a Mott insulator. So a certain amount of effort is trying to turn the iron-based superconductors into Mott insulators, because a Mott insulator is as strongly correlated as you can get, okay? The other thing is that you have got things like, you've never heard about it, there's something called hafnium, what is it? Chlorine, hafnium, what is it? Hafnium nitrogen. Yeah, hafnium nitride. Sorry, it's not jet lag. I'm just under the weather. So hafnium nitride, would you ever expect that to be a superconductor? If you put a little chlorine in there and you layer it, it's got a TC of 25 degrees. Okay, so it's believed the strong electron correlations, this covalent bonding helps you get there. That's something that Warren Pickett also is pushing. Anyhow, low dielectric constant, that's because if you put in large U's, you don't know how much they're going to be screened by the rest of the lattice. So a low dielectric constant means less screening. Do these different ideas contradict each other? Yes. We don't know the answer. These are some platforms we're using to try to define, and part of my research is trying to design new superconductors. And we work with theorists, and we just guess. Have we done it? No. But in any case, these things together will give you competing phases, which could give you emergent phases, and hopefully high temperature superconductivity. The rest of the talk, I'm just going to give you some flavor for the applications, and I won't go much longer here. I'll just kind of breeze through them because I don't want to keep you here too long. And as I've mentioned, if you make a room temperature superconductor and it can't carry current, it's not good for anybody, right? So that is a problem. And these high temperature superconductors, when they're so layered, they actually do have a problem carrying current because something called vortices, and they jump between planes, and it's hard to pin them, et cetera, et cetera. So we need to understand and control vortex matter. So maybe I should just say a little bit here. If you put a magnetic field in a superconductor, and I'll just say type 2 superconductors, which means interesting superconductors, you set up a vortex. Okay, that magnetic field is screened. The interior of that vortex is normal. It is not a superconductor. If that vortex is free to move around, that means you have normal material that's moving around, and you necessarily dissipate energy. So what you need to do is pin the vortices. A perfectly clean superconductor where the vortices are free to move around is a lousy current carrier. It's a lousy superconductor. So you need to find a way to pin the vortices. And on these highly layered materials, putting point defects doesn't do anything because the vortex jumps around. Okay, and I'll talk a little bit about that. How do you understand and control vortex matter? So those are things we're studying. These are all multiband materials. I'm just throwing these up here. These are just some of the things that we don't understand. Some of these things have multiple gaps. What happens when you quench and pinning low dimensions? This is something that's interesting. In all materials, if you create wires out of any material that's a superconductor, there is a glass ceiling. The JC is 20% of the maximum JC you can get, either predicted thermodynamically or you get in the best single crystals. Not understood. What is this glass ceiling all about? So that's something we want to understand. So barriers to superconducting performance is pinning the centers. So this is what I was saying before, you have to pin the vortices. How do you do that? And so we're looking at that in our center, besides understanding the physical properties, is different ways of pinning those. One of the ways we do it is is doing ion channels. So then you kind of collect the vortices. You run a channel through with ions, and now recently, in the past few months, we've done protons, and those make line defects, and you collect the vortices like a string of pearls, and so that pins them. I just want to point out the materials performers that as far as the high field limits go, that these high temperature superconductors actually have higher field limits than any other superconductor, okay, as long as you can pin the vortices. The workhorses, however, still remain niobium titanium, and in some cases where you need very high fields, then you'll go to an A15 compound. And so these are examples here, and here's examples here, et cetera, et cetera. So it's only the research magnets that use niobium-3 tin or niobium-3 germanium. I just want to point out that even though MGB2 is a simple S-wave superconductor, because it's a 40-degree TC and it's malleable, and it's kind of easy to work with, this is very promising for applications. And in fact, in Genoa, they have prototype MRIs made out of this 40-degree superconductor. Okay, it's going to be easier to cool. You can use liquid neon, and you can just use simple cryogenic cooling. This is a slide that I wanted to show you because my colleagues show it, and I stole it from George Crabtree. And it says cuprates, complexity enables functionality. That's what you tell your funding agents. Basically, this is so complicated. We have no idea what's going on here. There's got to be something good in here. So in any case, there are many, many distinct materials here. By the way, I think I've told you I've identified over 40 classes of materials that have that dome structure. There are 2 generations of superconducting wires, and we need a third. Can I have 2 more minutes? Okay, sorry. Okay. So the original first generation wires were silver tubes that you packed in bismuth, extruded it, brought them together, extruded, brought them together, okay? As far as flexibility goes, if you had a wire like this, you can kind of go like this. If you went like that, it stops superconducting, okay? They weren't that good. Most of what's used in ground still is this first generation. These second generation wires are awesome. These second generation, there's 2 ways of growing them. One is the Rabbit and one is the IBAD process. In any case, it's not silver. There's a teensy bit of silver there to help the growth. It's mostly Haynes alloy, and there was the YBCO in here. This is not to scale. It's really 2%, but these are flexible. They're just hard to grow. They're a complicated multi-layer technology, and there is a problem with C-axis critical current on these things. In any case, you can see what's happened. High temperature discovery, 86, and they start making wires, and they start learning how to make second generation. The first generation are in the ground. The second generation are in the ground by 2007, so that's progress. This is stuff that I've already mentioned, but the barriers are exactly what I said. Cost factor, and we still haven't shown reliable multi-year application. These are in the ground today. These are transformer stations and in-ground wires. I will also say that, well, this is accommodating renewables. We don't want this, we want this, and we have to transmit that electricity. One of the plans would be to put in-ground DC superconducting cables. We're not going to rip out the existing high-tension AC cables. We're going to put in-ground to work in parallel. And that would be a direction to go, an interstate highway for electricity. And one of the reasons why that's a good idea is because, at least in the United States, for some historical reasons, which I don't understand, we have 3 separate, not connected grids. There's the Northeast, the Northwest, and the Texas grid. They're not connected, and they're AC. How do you connect them without losing power? You've got phases to worry about. So the plan would be, but we lost the funding, we're hoping to get it back, is to invert down to DC in superconductivity, then convert back up to really connect these across. But we've got a ways to go on that. The turbines are great because they're 5 times less the weight, and that's just the first prototypes. Turbines are now the size of 737s. So weight becomes an important factor. So superconductors are going to have a tremendous impact on those turbines. And once we make these kind of turbines, we can put them offshore closer to the population centers. The SMEs are fascinating, and these are these superconducting magnetic energy storage. By the way, all this technology existed in low TC with GE in the 60s. This is just reapplying to the high TC. The SMEs is you can just collect the energy into a magnet, into a toroid. Why is this so great? And by the way, some of these are in ground in Michigan right now being tested. Let's say you want to take the energy by photovoltaics. Photovoltaics not only have the day and night problem of collecting solar energy, but they're also quite noisy. So this actually moves faster than this. They're actually pretty fast. So you can collect all that noisy photovoltaic energy and bleed it out smoothly day and night into the grid. So we're working with Superpower and Brookhaven in trying to develop better quality SMEs. Right now, that's pretty pitiful, but we just got started. So we have our grand challenges, and that's our plan for the future. And I'm going to end up with 2 minutes here. Okay, this is 1 minute of my own research. So as I mentioned, there's a ubiquitous phase diagram. This is the line that we added here. Okay, so our measurement is point contact spectroscopy, where we inject electrons into a material and measure the scattering. This has been used for many years to look at phonon scattering, magnon scattering, even Kondo scattering. And it's been looked at Andreev scattering, where you look at reflection due to, which is understood because we understand the BCS theory of superconductivity. What we found in the last few years is, in fact, for instance, this material, this is an iron-based superconductor. This is cobalt substituted for the iron in something called the 1-2-2, barium, iron 2, arsenic 2. And we see this intense excess conductance that exists in certain places. And that intense excess conductance in this point contact exists where other people have measured something called nematicity. So we found this easy way to find that, in fact, there are strong correlations that exist there, and we could measure them directly with this measurement technique that we thought was old, but is being applied to something that's never been applied to before. So I'm going to finish now in saying superconductivity isn't dead yet. We're not dead yet, and our goal is let's make better superconductors for fundamental research and for applications. So I thank you for your time.
Great. Thanks. Comment and question, please.
I went too long.
I have a comment. One point that you didn't make is connection between the chemistry of a material on the one hand and what it actually looks like on the low energy scale, what type of interactions are effective between the electrons. And that is a big hang-up. For example, there are, I think, some interesting ideas around how
Wait, can you all hear this? Because this is really important. Can you all hear Professor Rice? Yeah.
But, for example, Warren Pickett has a nice idea that by getting a material where different parts of the band structure couple strongly to different phonons, as is the case, for example, in magnesium diboride that you mentioned. Right. If you could repeat this through different parts of the Fermi surface, coupling to many different phonons, you could get a very high superconductor. So that's a nice idea. The question is, how do you realize that? I mean, how do you make the connection between the model that you were looking at for the interactions,
so
electrons and the chemistry that goes together to form the material in the first place?
I have another 25 view graphs on how we think we're going to look for new superconductors, and I think what you're saying is really important. So now that I've recovered from a conference I ran in Washington a couple months ago, I'm not quite recovered, we're going to start having more of these get-togethers and bringing chemists and geologists and certain kind of people together, and just not the same old people that we've gotten together and discussed before, people with really innovative ideas, and start including people like Bob Kava and also chemists. So I've been working with a guy at Illinois named Hirata, who now knows how to, is a chemist, and can calculate things that include some strong correlations that I never thought was possible. So I think Warren's ideas and some of these other ideas, we need to bring them together. And yeah, I don't know how to realize it, but that's the grand challenge. So help me out here. Thank you for bringing that up. Yeah.
Please.
I guess it's more of a philosophical question, but you said that perhaps you'd have a third or fourth class of HighTC superconductor, but do you really think you can ever really break the barrier of TC to really get it up as far as room temperature?
Do I think we'll break the 165-degree barrier of TC?
Yes.
Absolutely. No, we don't know what limits TC, and I can show you a paper that I hung on my wall for a long time after HighTC was discovered, where there was a paper written by our colleague Chandra Varma that 40 degrees was the limit, right? And it was the limit on electron-phonon coupled three-dimensional superconductors. That was the limit. We never thought of this kind of spin fluctuation mediated things near, you know, an antiferromagnetic or ferromagnetic phase transition. We never thought of that. So there's probably things like looking what Warren Pickett wants to look at, et cetera, that we just never thought of. Maybe they'll be discovered serendipitously and we can just keep mixing materials, or maybe someone will figure it out. But why would that be the limit? The fact that we haven't discovered anything higher since 1988 doesn't mean that we're not going to, right? We don't know where to look. Periodic table is big, right? It's big, and there's, you know, so we have like 108 different elements, and then how much of each one, and then pressure and temperature, and how do we grow them. So, you know, we can put like 5,000 monkeys in a room, like in 1, 2, 3 infinity that George Gamow talked about. If you put them in a room long enough, they will type out all the works of Shakespeare, right? It's going to take too long to do it that way. We're going to have to be a little more clever. So people like you, who aren't burdened by what we already know about superconductors, are the ones that are going to tell us how to do it. So. Maybe. Maybe. Well, it's interesting that the coated conductors of YBCO carry more current than the lower TC superconductors. Yep. Well, okay, so I guess I'm not going to say that I expect a room temperature superconductor to transform the grid, okay? But why can't we make better superconductors that are 150 degrees that we could make better wires for? And I think that's something that I try to stress here, and people don't hear that. I know that Alex Malazimov keeps writing me nasty letters, even though we get along all the time, because I'm always stressing TC isn't enough. That's why I stress what John Hume did. We wouldn't have MRIs without John Hume, right? HighTC gets Nobel Prizes, HighJC saves lives, okay? HighTC gets Nobel Prizes, HighJC may help us in global climate change. So I agree with you. So let's make better superconductors, maybe higher TC, and maybe other kinds of structures that would be better JC.
Of course, I could, while someone is thinking about the question, I can just comment that, as you know, the new classes of the iron-based superconductors, in terms of JC, look totally amazing.
Yeah.
They're not published yet, but they're just amazing. These materials, they carry current up to 100 Tesla. You don't have another magnet to measure these magnets. That's how good they are. So there's hope there. They have to be better, not just high TC.
And the iron chalcogenides are fairly malleable too. So the iron pnictides are still pretty brittle, but the chalcogenides are pretty malleable, and those are very promising. So.
Anyone else? Of course, there's a cultural comment. High temperature gives the prices, and the high chase makes money. And that's a little bit the bias that we tend to have in academia.
Right.
Any other comments, questions? If not, let's thank Laura again. Thanks a lot for a wonderful talk.
Thank you.